Okay, I'll start with you today this video about the curve fitting and SP lines. So curve fitting, curve fitting, and SP line. So let's start with curve fitting. Curve fitting. So we use least square, or what you call it, least main square, i.e. minimize the sum of square errors. Let's see what that means. If we have, let's say, some test values, experimental test values, or we have x and we have y and we have some points. Okay, these are experimental points. So we want to see which line better fits this value, something like this. Okay, this is a line. So we want to fit these lines. Usually, the function y, I, is equal, let's say b0 plus b1 x I plus an error ui. So this is, we call it error or disturbance. Okay, so this is the linear fit, but we have a disturbance with it. So we want to find b0 and b1 that minimizes sum of ui squared. Okay, when we say y ui, it means that we have y1, y2, y3 until yn. Okay, is equal to b0 plus b1 times x1, x2 to xm plus u1, u2, un. So these are measurements. This and this are measurements, and this one is the error. Okay, and these are constants. b0 and b1 are coefficients. We want to estimate these coefficients. Okay, now we assume assumptions that the mean of u equal 0 and variance of u equal sigma squared. Now we'll come to this later. In your notes, you'll find out how we determine these coefficients, but I'll give you here a general framework that you can apply it, okay, in matrix form, okay. If you have many parameters and many measurement points. In C, for example, y equal b naught plus b1 x1 plus b2 x2 plus b, let's say, m xm plus u. Okay, here x1 x2 x3 until xm we have multi variables. Okay, b0 b1 b2 to bm are the coefficients and u is the disturbance, y is the output. So you have the system where you have several inputs, x1, x2, and it will give you an output, but you inject with it also disturbance, or measurements. We call it measurement error. Okay, so this system has parameters b0, b1 up to bm. Let's say here xm, bm, and we want to determine experimentally what is these coefficients b0, b1 up to bm. Okay, now you may have several variables x1, x2, to xm, or you may have only one variable but different functional forms. For example, y is equal b0 plus b1x plus b2x squared plus you may have b3 root x plus u. In this case, we have only one variable, which is x, one independent variable, which is x. So x equal independent variable, while y equal output or dependent variable that depends on the variable x. And here we can say we can name x1 equal x, x2 equal x squared, and x3 equal root x. Okay, so this function will be linear in the parameters. You see, it's b0 plus b1 times x plus b2 times x squared plus b3 times root x. So though x, it is nonlinear in x, but it is linear in the coefficients. We don't have multiplication of coefficients. b2 x squared. So if we assume that x squared is another variable, which is x2, then it's b2 times x2, okay? Which is x squared. So we say this function is linear in parameters. And how we find b coefficients, okay? Now, let's say that y equal b naught plus b naught is we call it intercept plus b1 x1 plus b2 x2 plus bm xm plus disturbance u. Okay, now we call b naught, we name it as intercept. For example, this one here, this parameter, this is b naught, and the slope is b1, assuming single parameters. Okay, we have only x1 and y. So b naught we call it we name it as the intercept. Okay, We can put this in a matrix form. Y equal x times x, xx, we'll call it xx times b plus u. What is this xx? Just another variable. Xx is 1, 1, 1, x1, x2, okay, x1, let's say j, x1, 2, x1, 1, x1, 3, and so on. Here x2, 1, x2, x2, 2, x2, 3, and so on, okay? Now these are measurement points. For example, x11 is the first measurement of x1, x12 is the second measurement of variable x1, x13 is the third measurement of variable x1, and so on. Similarly, x2 is variable x2, but x21 is the first measurement of x2, x22 is the first measurement of x2, x23 is the third measurement, and so on, plus vector u1, u2. This represents disturbance of the measurements. The disturbance in measurement 1 or the error in measurement 1, measurement 2, and so on. And it will give you y1, y2. This will be y1, y2, and so on, okay? Assume that we have n measurements. So here 2x, 2n, x1n, okay? And here 1, okay? So this will give you this times, of course, let me just correct that, okay? Times the B coefficients, okay? This times the B is B naught, B1, B3, assuming that B2, assuming we have two variables here, plus U1, U2, okay, U1. Now, if you look at this, B is a matrix, it's a vector matrix. B naught, B1, B2, so it's 1 times B naught, 1 times B naught, times B naught is the same, okay? This XX represents this matrix, okay? The first column, we have it once. The second column is the measurement of the first variable. The second column is the third column is the measurement of the second variable, and so on. So we can put it in a matrix form that XX is equal 1, 1, 1, 1, x1, x2, okay, 1, 1, x1, 2, second measurement, x2, 2, second measurement, and so on, okay? So this will give you the formula matrix Y is equal XX times B plus U. Now B, we want to determine, okay? Now, in the general form, we want to minimize this U. So U is equal what? Y minus XX times V. As this is a matrix. We want to minimize the square of that. So what we do, we say U minus, we said the main of U is 0, so we forget about its variance. Now what we want to minimize sum of UI squared equal what? And minimum. okay? This one is equal, sum O is equal U as a vector transpose times U, which is equal U1, U2, UN times U1, U2 till U1. This will give you the same. The sum of UI squared is U transpose times U, okay? Will give you this sum of the sequence, okay? We want to minimize this. So what we say, minimize U transpose times U, which is equal Y minus XX B transpose times Y minus XX times B. Okay, we want to minimize that. Now, if we multiply this, what you will do? What we will get? Y times Y transpose times Y minus X B transpose will give you B transpose times XX, and we have another one, so you'll get 2 minus times plus, you'll get B transpose XX times XX transpose, here transpose also, okay, times XX times B, okay? You will get that. Now minimize this, we take derivative of U transpose with respect to U. We derive it with respect to B. This is a constant, Y transpose Y is a constant. This one, let me correct that, we have a Y here, okay? We have a Y times Y plus, okay? We forget this, Y times, this XXB transpose times Y, okay? Now, the derivative of this here will give you, with respect to B, will give you 2 minus 2, okay? X times X, it's not the X times X, it's XX, this is a variable XX, okay? Times Y plus, now this one will give you twice X transpose X. Here we have XX transpose also. XX X. Okay, let me correct this just. What we have, X is a variable, what we call it, transpose, okay, times B. And we equate this to 0, okay. This will give you least main squares of U, okay? So we solve this equation. We solve this equation. We equate this minus 2x transpose times Y plus 2. Here we have let me correct that again. Here we have, we forget the X, the other X, we have X times X, XX, okay, times B. Let's correct that. So here we have X transpose XX. XX is just a matrix, okay? Just I name it XX. It's not X times X. It is just this matrix, okay? Ones and measurement of variable 1, which is equal to measurement of variable 2, which is x2, and so on. Just I named it XX, okay? times b, and this is equal to 0. So we can determine b is equal, we take 2, will go with 2, so what we have, xx transpose times xx, we invert it, times xx transpose times y. Okay, this is the general form. We'll obtain that matrix. Okay, so this is, we can use it and generalize it. Okay, what we need also to find the variance of these coefficients. Variance of u is equal to sigma squared equals sum of ui minus main of u, and this is usually 0, okay, squared. And we divide by n minus 1. Okay? You divide this by not by n minus 1 will give you the variance. Okay? This is the estimated variance of the error. Okay? So this will give you a variance of b. The variance of b, I want to just you memorize what is the variance of b. Variance of matrix B is equal, we take xx transpose times xx, we invert that, okay, now times x transpose times something, I'll tell you about it, times xx, okay, xx transpose here, xx times the same xx transpose xx inverse. This is the same here, x times xx transpose inverse, and here xx and here xx transpose, and this here we can put it as sigma. Here sigma u is the variance of u. Here sigma u squared. Okay? We do that. Since this is a constant, we can say this is simply x transpose times xx, okay, inverse, times sigma u squared times xx transpose times xx times x transpose times xx inverse. Okay, this will go with this, so you get finally sigma squared, okay, yeah, xx transpose times xx inverse. This will give you, it's the right name for it, we call it covariance, okay? Since B is, it will be the variance of, if we have only one B, one element, but we have many elements, we call that variance covariance, okay? Let me correct that for you, okay? It's covariance. We call it covariance. Okay? Now, what is a covariance? If we have, what is the covariance? If we have, say, two variables, okay, two vectors, v1, v2, v until vn, okay, and we have another, let's say, h1, h2, hn. These are two vectors, okay? This is vector 1, vector 2, Okay, then what we have, the variance of V1 or variance of V is equal sum of VI minus المين average. This means المين minus mean squared, and we divide by 1 n minus 1. Okay, this is the variance. Similarly, variance of H is the same 1 over n minus 1 sum of H I minus المين of H squared. الcovariance between V and H is equal 1 over n minus 1 sum of V I minus V main times U I minus HI minus, can you correct that? Okay. VI minus المين of V times HI minus المين of H. Okay, this will give you the covariance. It will be a matrix of M by M. In this example here, it will give you a 2 by 2 matrix. Okay, let me just demonstrate that through MATLAB to you, so you know what we are doing. Okay, you go to the MATLAB video, because I do it in, it's the same speech, but I'll show, it shows the MATLAB frame or MATLAB screen. Let's say if we have, for example, U1, U1 is equal, let me make it a random, okay, a random vector. Let's say random, let's say 100. I have 100, vector of 100, 100, 1. This is a vector, okay, but it has a random value. Let's say 0.5 here, 0.5 minus, so it can give me also negative. This random here, this here will give me only positive, okay, from -1 to 1, but it's a random vector. So if I take 0.5 minus that, it will give me negative and positive values. Okay, so this minus that, okay, let me see this, minus this will give me a U1, okay? This will give me, okay, a vector U1, and if I take another random variable, let's name it U2, okay? So if we check U1, what is U1? You see it's 100, it's a vector, okay? If we plot U1, okay, if we plot, let's say U1, you'll see that it plots, this is the random vector. It has a main nearly 0. The main here, the main is nearly 0, okay? The main is nearly 0, okay? But it changes because it's a random vector, okay? Now, if we look at U2 also, let's plot it this way. 1, because we have 100 values, so 1 to 100, okay, U1 will give you that one, and let's look at U2. You see, they are different. 1 to 100 and U2, okay, you'll get these two vectors. If you look at them carefully, we have two different vectors, okay? This could be errors or disturbance, okay? And now let's calculate the variance. In MATLAB, we say variance of variance of u1, okay, it will give you here is variance of u1, it will give you 0.088. This is sigma squared of u1. If we do it for u2, okay, u2 is a different vector, 0.0839. If you calculate it this way, sum of u1 minus main, because we generated the vector u1, it may have a main value, so we must subtract it. Okay, u1, and we square them. Okay, this is a vector, we square them. Sum of squares of u minus the main of u. Okay, if we square this one, okay, and we square them and take the sum, will give you that. We divide that by 101, because n is 100, okay, so n minus 1 is 99. So 1 divided by 99 times that one, it should give you the variance. It's the same as the variance of u1, calculated by MATLAB. You look at it. If we do it for u2, you'll get the same. Okay, if we do this for u2, okay, and here main of u2, you'll find the variance of vector u2, which is the same here. Either you do it in MATLAB or you do it yourself, you will obtain the same figures. This is what we mean by variance. Now, covariance between u1 and u2, we can do it this way. Covariance, so COV, that's in MATLAB, covariance between u1 and u2. u1 and u2. It will give you a matrix, 2 by 2 matrix. And we can do it the same way. We can say it's the sum of this. Let's put it, okay? We don't have a series here, and we don't, okay? The sum of the covariance between, how we do it, I'll show you. You take u1, u1, we said what we want, u1 minus, okay, minus main of u1, that's one vector, minus the main of u1, okay. So this will give you a vector u1, okay, and you have with it, we'll put it in a matrix form. This is a matrix, okay? This is a matrix, okay? And we have another matrix with it, which is a matrix u2, okay? u2, or vector u2, minus its main of u2. How you calculate it, I'll show you. Main of u2. So actually, if we look at this one here, let's remove the sum here. We look at this one. This is a vector. This is the first column here is vector u1. This one is vector 1 minus its main. And this is vector 2 minus its main. Okay? Now, if we take them here, okay, this is a matrix. Now, if we take the transpose of this one, we'll give you a row vector, 2 columns. Now, if we multiply it by the vector itself, transpose times the vector, I'll show you how. Just you do it. We remove this transpose. you'll get a 2 by 2 matrix. This multiple times that, you'll get a 2 by 2 matrix, okay? If we divide this by n minus 1, which is 99, 1 over 99, you'll get the covariance matrix. So you get this covariant matrix. You compare it with a curve, you will, so it's the same, okay? That's the way how we calculate the covariance matrix if we want by hand, okay? Now, going back to this one here, we know how to calculate. This is one way of calculating the variance matrix. Now, we have two forms, okay? Okay. Now, we have two forms of statistics. One is standard, two is robust. I'll show you what is the difference exactly between these two. The covariance matrix of B is equal sigma U squared times XX transpose times XX inverse, okay? This is the standard, okay? This is this one here, okay? Now we have robust. In the robust one, we take the original form. The covariance of B is very important. We take this matrix here, so it is X transpose times XX inverse. Then we take XX transpose. Then we take XX here, okay? Then we take XX transpose times XX inverse. This one is the same as this one. Here XX transpose, here XX, okay? Now this matrix here, we don't take the variance of the error, the sigma, directly. What we take, diagonal of U squared, which is equal U1 squared, U2 squared, U3 squared, and so on, diagonal only, okay? If we do it this way, we get robust, okay? So this is robust statistics, okay? So there's a difference. There is a difference between standard and robust. Robust is more accurate, okay? Now, so from that, now we know how to calculate B equal what? Which is X transpose times XX inverse times XX transpose times Y, okay? This will give you B. That's B equal B naught if we have just a constant, B1 if we have just one variable, B2 if we have two variables, and Bm if we have m variables, okay? So we know how to calculate B. Also, we must calculate the covariance of B, whether standard or robust. Now, if we take diagonal of the covariance of B, it will give you, and we take the square root of that, it will give you standard errors. Okay. This will be the standard errors. Okay. Now, if we use robust, we get the robust standard errors or robust errors. If we use standard covariance matrix, okay, we use so if we use this one, okay, that's the standard matrix. We get standard errors. If we use the robust covariance matrix, this one here, we obtain the robust standard errors or robust errors, okay, diagonal of that. Now, how do we know that the coefficients we calculate? Coefficients will be, how do we know whether they are good enough or not in statistics? Okay, what we define significance of any element B, let's say BI, if we divide that by standard error, okay, I. Now let's go, what is BI? I could be 0, B0, B1, B2, depends on. And here it's the same, the diagonal element of the square root of the covariance matrix. We call it standard errors, okay? Which is equal to SE, okay? So diagonal elements is I0, 1, 2, and so on. Now, this, we name it significance. For 5%, okay, or 95%, significance means a 5% error, okay, B divided by SE, I greater than, say, 2.5, okay, approximate. If this turns out to be, we calculate this one, B over standard, turns out to be more than 2.5, we are happy, okay? We say it's okay, no problem with this, with our estimate. The way how we estimate the coefficients B. This is named as the significance, okay? Now, there's another criteria which is called confidence interval. What is a confidence interval? Okay. Usually we find the 95% confidence interval. What does it mean, 95%? So if we calculate, let's say this is B, okay? B0, B1, B2, it doesn't matter, okay? Any B's, okay? Now, since we assume it is sort of a random variable, the one we calculated, it has actually a confidence interval. This we call it 95% confidence interval, okay? يعني if it is, for example, 2, it could be 2 plus something, 2 minus something. There is an error, okay? So this is a confidence interval, okay? It's not exactly, if we calculate, for example, 2 here, or say 5. It's not exactly 5. If we take another measurement, it could be 5 point something. We take a third measurement, it could be 4 point something. So it is within an interval. We call it this confidence interval. How we calculate that? B plus and B minus. So it's between these two values, 2 times approximately, okay, 2 times approximately the standard here, the standard, okay. So in this region here, this is minus, and this region here is the plus. So plus 2 times standard error, and here minus 2 times standard. So the B coefficient will be between these two values. So this is B here, okay? So this is B minus 2 times standard error, and this is B plus 2 times standard error, okay? 2 here is for a 2 point, for 5%. If we go to different 90%, these values will be different. But 95% is practically chosen always in all applications, okay? Now, so the B we obtained will be between these two values here, okay? Usually, so we call this interval is confidence interval. I'll show you an example how we calculate that, okay? Meanwhile, we can say B is equal, say B calculated plus minus an error. This error, let's say 5% error. This error here is actually SE times 2, but we divide by B, okay? Because we want to calculate the percentage. So here is 2 standard error here. What is the percentage? Okay, related to B, so we divide that by B values, okay? Now, it's better we go through the program in MATLAB and I show you how we do that, okay? Now, if we go back to MATLAB, okay, I have, let me open the file, okay? Let me just set a path. You do add a folder here. If I add a folder for your course, it is, I named it EENG 205 online, okay? We select that folder, okay? Now we added that, okay? Now, let me just open that file. Already I will also, okay, where's that file? Open here. It is CurveFit, okay? This is a file curve fitting, okay? I will upload this file for you so you can practice it. And here, we assume that it's curve fitting, okay? Curve fitting using a minimum least square error, okay? Here, intercept is 1. If we have intercept equals 0 if we don't have an intercept, okay? And here, I will actually, if XX is equal here, 1, 1, 1, and here X, okay? So here 1, if we have intercept, okay? Otherwise, it's not there. Otherwise, XX equal X if we don't have any intercept with no intercept, okay? Something like that, we don't need an intercept if we want, for example, to find a resistance. A resistance, we do measurements of V and I, and we try to obtain what is Ohm's law. We know that it should go through 0, so no intercept here, no intercept. Okay, so we delete just the first column in here. We don't have these ones. That's what it means. Or we can convert 0, but we have to delete. 0 means no intercept, okay? Now, I defined an x from 0 to 2 in steps of 0.01. So that will be something like 200 measurement variables from 0 to 2. Okay, you can change that. Now, I define x as x squared and square root x, which means that I made x1 equal x, x2 equal x squared, and x3 is equal root x. Okay, so this is a nonlinear function. It has a vector 1 or variable 1, which is x, this one, and variable 2, which is x squared, and variable 3, which is x square root x. You can add variable 4, for example, exponential, and so on. So what we have here, three vectors, three variables, x squared, and square root x. Means we'll be having b1 and b2 and b3, and if we have an intercept, that would be b0. Okay, we generate here an error, see, random, an error of a value 2 times. You can adjust this one to, you can make it a 3, less, and so on. Then we generate y. Y is sort of a linear combination, a constant 10, that should be b0. We want to estimate this, plus 3 times x, which is 3 times x1, plus 2 times x2, plus, which is x squared, okay, x2 plus x1, all 1, it means x all 2, okay, it means that it is x squared, and so on. And we have the root of that x1, we could calculate over that. We add to that vector this disturbance here. So it won't be exact, this value depends on this disturbance. Now, if intercept is 1, we add 1. The columns, you remember, this column 1 to the vector x. If we don't have an intercept, we don't change x. So xx is the same as x, okay? Now, how we calculate the coefficients? It is xx transpose times xx, we invert that, and then times xx transpose, then times y. This will give us, will be coefficients. If we want to estimate, we call it y hat. So what is the estimate? I'll show you, okay? Y is equal x times b plus u. So y estimate is xx times u. So this is estimated y. Now u is equal the original y, or the measured vector y, minus y hat, or minus estimate. So that's the error. This is y hat, the estimate. Okay, this is the error, u hat, estimated error. Okay, so this is u hat. This is, we call it estimated error. Okay. Now, from this estimated error, if we determine the mean of u, the main value of u here, we'll find it 0. Okay. Now, how we determine the covariance of this matrix of the coefficients? We have 2 standard covariance and robust covariance. The standard covariance, we take the variable with the variance of estimated error, variance of u hat, okay, times the inverse of x transpose times x. This will give you the standard covariance matrix. If you want the robust, as I described it, you take the diagonal of u hat squared, okay, and put it in the middle here, okay. That will give you the robust standard errors. Now, what is the standard error, we take this will give you the robot standard or robot covariance matrix. If you take the diagonal of these matrices and take the square root, you obtain the standard errors. Okay, so standard error for the standard form would you take the standard square root of the mentioned the specified covariance matrix, the diagonal elements of that. If you want the robust, take the covariance diagonal elements of the robust covariance matrix. You want to calculate 95% confidence interval. You take B minus standard error times 2, okay, or plus. This for the standard, this for the robust, okay. B is the same, okay. If you want to calculate significance, to give you the significance errors 5%, you divide B by standard error. This will give you for the standard form, this for the robust form. Then this one is just to print out the results, and here we plot, okay. Now let's do that for this vector and see what happens, okay. Now we have curve fit, okay. This is the curve fit. Now let's look at that. Now here are the measured values with the disturbance, okay. The red color line is the curve we fit. You see it's non-linear in X, but it's linear in parameters or in coefficients B, okay. So that is let's look at the results here. Standard coefficient statics. These are the B's. B0. This is B0. This is B1 because we have 3 variables. This is B2, and this is B3. This is B1 for X. This is B2 for X squared. This is B3 for square root X. You can add to that. This is the standard error, okay? This is the standard error, okay? This is the significance, which is B divided by. So if the significance is more than 2.5, we are high. So for example, for B0 is 30, so it is good. For B2, it is 8, good. For B1 and B3, it is small. So we can approximately say that instead of calculating that, we could assume that these variables are 0. And this is the percentage error, okay? So this is 95 confidence interval, if you look at it. This is B, but B is actually between 2 values, B minimum and B maximum. It's between 9.07 and between 10.34. So this is the 95 confidence matrix, okay? Or 95% confidence interval. Similarly for this one, for this one, for this one, okay? And this is the same for robust, okay? They differ a little bit, but it's more accurate, okay? Now let's look at some of what we have estimated U hat. This is U hat. U hat, okay? This is U hat, okay? If we plot, let's say U hat, so this is U hat, you see, it should have a main, a zero main value. So look here, zero main value. Let's add just a line width, okay, give it 4, let's see how it looks like. 4, okay, this is 4, it's too much, okay. This is actually the errors, okay, the estimated we can calculate the variance over u hat, okay? It is 0.315. That's the variance of the error or the estimator. If we calculate the mean, it should be 0. Mean over u hat is almost 0. It is 10 to the power minus 12. Okay? Now, let's just run it again, curve. Okay? Let's look at the measure values, and this is the fit curve. It's good enough. Okay? It has a bit large errors. Okay, now if we just go and change, because we gave the errors we made is a bit high. Now here is u. Let's just divide by 10.2. We reduce the error and see what happens. Perfect. You see here, we reduce the errors. Errors has been reduced. We have less measurement errors, which means that the fit values would be better. Look at them here. This is B. This is the standard error. It has been reduced. Standard error fit reduced. We have better. You see the significance here? All of them above 2.5. And this is a 5% error. Okay? For the both and standard. If we make the error 0, what will happen? Let's make the error 0. So if we don't have an error 0 here, we expect that it will give you the exact p values. We expect that B0 will be 10, B1 will be 2, B2 will be what? -1, because U is 0. Okay, let's see. Perfect. You see, you get the exactly. We don't have u is zeros. You see, we don't have u. Okay, y hat and measure is the same. You see here, b. This is b. The standard error, of course, you divide by standard error. You know, standard error is. If we look at this, for example, what is the standard error? Is the covariance matrix. And to give you minimum zeros. You don't have an error, 0 standard error, you see. If you look at this confidence matrix, it will be the same. This is B, but B minimum and B maximum is the same. 10, from 10 to 10, from 3 to 3, from 2 to 2, from minus, it means you don't have any error, okay? You don't expect usually this in measurements, but what you can do, instead of doing that, you give 0. You give a small value to the error, very small value, and see what happens. Okay, again, it will give you very exact fit. Okay, we look at it. You look at the values here. You see, significance is very high. It means that's almost okay. And you can change these values. Go to 0.01, for example, larger, and do it again. Okay, and curve it. You have it here. Okay, you see the significance is very high. Standard is still low. You see the significance here. Okay, and so on. And you can add practically somewhere, say 0.1. Usually it happens at least 10% an error in the measurements. You have it, okay? And if you do curve fitting again, you can have this, okay? And you see, still we have a good significance here. Small standard errors. And you can, instead of 1, say, I'll go to 1. Okay, 1 is a bit high. You see, these are the errors here. 1, okay. And you have still standard small standard. But if you have more errors, then this significance value will reduce, okay? Let's say, for example, if we have 10 times, okay? And do the fitting again, you see? We have too much errors, you see? The error is huge. But nevertheless, we have drawn a good curve of that. Let's look at the values we obtained from that. Okay, these are the values obtained. Instead of 10, we have 7 point and minus and 4. Okay, but look at the significance value. For B naught is good. For B2 is also good. For these ones, which means that we should not bother about till B1. We should not bother about till B3. B naught is okay because the significance is good. B1 is not that good. Okay, it means we can neglect it. We can make it 0. B2 significant is fine. B3 significant is small, so we can neglect it if we want. So we assume that in this here, what we have really is B naught and B2, sort of a square value, okay? It will also fit it nicely, okay? So that's the, regarding how we do it. I want you to go through the notes and find out how we have done that in your notes. And this is a general form. I want you to practice it, okay? And do it as a general form by transforming any function to linear. For example, if you look at this note, if we have, let's say, y, for example, is equal b naught exponential of, let's say, b1 x. Now it's non-linear. We can transform this. We say ln y is equal ln b naught plus ln ab1x. Okay, this will give you ln y. Okay, as in the notes, we can transform this to a linear form. We say ln y, and here ln y equal ln b naught. Let's say it is let's name it as a b hat ln b plus b1x ln e to the power of x. So here this means this b hat, okay, if we use here a new vector, say y1 here, and here is b hat, and here plus b1x, and we estimate it as a linear function, okay? But we don't use ln y, we don't use y, we use ln y. We name it y1, and this here is equal to ln b naught. So b naught is what? A to the b bar. So we estimate, as you have in the note, we estimate actually b bar, and then we estimate b naught as equal to exponential b bar. So we transform this exponential form or function to a linear form by taking the natural logarithm of both sides. And that is very easy to be done, okay? I want you to practice this one, okay? And see what is the difference, how we calculated confidence intervals, okay? How we calculate the covariance matrix, both robust and the standard. And if we take that square root of that matrix, it will give you the standard error. Let's look at that. what is the covariance matrix standard, for example? What is the covariance of B? Already we have calculated standard, for example, the standard form, okay, S. So it is a 4 by 4 matrix. Why 4 by 4? Because we have B0, B1, B2, B3, 4 variables, 4 coefficients. So we obtain the covariance matrix, the matrix 4 by 4. These are the diagonal elements. We take the diagonal elements of these ones, will give me the standard errors. So what is the diagonals? We take diagonal of the covariance of B S, it will give me this is the diagonals. 2 point, here is 2 point, okay? 41, that's 41. Now, if we take the square root of that, square root of that, it should give you the standard errors. It's very important to calculate the standard errors of that, okay? So that's 1.6, 6 point, 1.4, 6 point. If we look at it here, we have it there, 1 point is 6 point, and so on. If you want the robust, just change that. R will give you the robust one, which is almost the same, similar to that. So it's important that we know how to calculate the B coefficients, how to calculate the covariance matrix of the coefficients, and from that we obtain standard errors, and how we calculate 95% confidence, okay, confidence interval, and how we calculate error and significance. You may have studied some of that in statistics course. You have taken mathematics, okay? Usually they give you these sort of things. If you take the random variables, or if we take what we call them reliability, or okay. They teach you there how you calculate the mean value, the variance, the covariance, standard errors, significance, and these things, okay? Now, at least I want you to know that you know this for linear. This is very important. What we call this linear regression, okay? I'll just write it to you down here. What we have done is what we call it linear regression. Okay? Linear regression, where we find where y equal b0 plus b1 x1 plus b2 x2 plus u. Okay? So finding b0. X equal regressors, we call it in statistics regressors, okay, and Y is regressed, okay, or instead of regressors, we call them independent variables, or dependent, independent, okay. So, B, very important, covariance of B, very important, standard errors of B, okay. From this, we'll give you standard errors, and 95% confidence interval. I want you to practice this from that program Just I will upload it to you, both in Blackboard and through the WhatsApp application. Okay. What is left? This is very important. Plus the notes, you go through that in the notes. Okay. So the curve fitting using linear regression, okay, is very important, and it's used everywhere in practice, in engineering, in electrical, in mechanical, in medicine, in economics, in physics, in chemistry. We use this least mean square error, okay? And this is the way how we calculate the coefficients and their significance. When we say significance or statistics significance, we mean what is the covariance, what is the standard error, what is the 95% confidence interval, and so on. Okay. What else I need you to know regarding curve fitting? Probably this is the most important. Okay, let's just do something through MATLAB again. Let me just add something here. You can practice. Here we have what? X square root x. Let's have we cannot divide by because we have 0. Let's give something else. Let's say exponential, another variable, let's say exponential of x, for example. Okay? So it means in this case here, what we find? This is x1, this is x2, this is x3, and this is x4. So we have 4 variables now. Okay? We do the same. We can just reduce this one here. Let's say here 1, for example. Okay, the error is 1. We do the same here. Okay, we can add something to it. Let's say plus. We want just to measure the right thing. Let's say minus 2 times exponential times the exponential of x. Okay. Exponential of x, or you can put minus x, okay? X here, you can put minus here, doesn't matter. So, and we assume we have an intercept, that's why we put 10 here. And we do the same, and let's see what happens, okay? Let's just run this program. Curve fit. Okay, there is a mistake here. Definitely, matrix dimensions must agree. Yes. I think square root of x, or x here. X is let's see, 10x1, because we have already had an x here exponential, so we want x1 or 1. It's not that x exponential of the first one, that's 1 here. Okay, x all 1. You can practice that. Okay. Now, just generating that, okay, we get a curve like this. You see, these are the measurement points. We get a curve like this. It's best fitting that curve. Okay. Now, if we look at the coefficients we obtain, this is B naught. Now this is B1, this is B2, and this is B3, and this is, you remember we put minus 2, we put minus 1.84. Why? Because of these errors. Okay, so this coefficient belongs to the exponential form, B4, 0, 1, 2, 3, 4. So this is B4. Okay, and here I'm showing it also in the tablet, in the keyboard, tablet keyboard. What we have done here is y we assume equal b0 plus b1x plus b2 x squared plus b3 root x plus b4. Okay. Exponential of x. Okay. Now, what we have done here is x1 and x squared is x2 and x root x is x3, and this one here, e to the power x, is x4. Okay. So b0 to b4, these b's we have calculated here. Okay. These b's here. Okay. And these are the standard errors of these b's, and these are the significance of them. If you reduce the error, you will get higher values here. If you increase the errors, you will get lower values. And this is a 5% error. This is the confidence, the 95% confidence interval. Okay? You can practice that. But this is the general form. What I want you to keep in mind, this is how we calculate LB. This is very important. Okay? This is the B. You first design this XX, and then you just update it. XX, you design it just, it is the value x1, x2, x3, x4. And if you have an intercept, you add to it once in the beginning. Okay? If you don't have intercept, then it is the same. Okay? So this is the first video. I want you to study this video carefully, practice this program after I send it to you. Meanwhile, see the video, the other video, the MATLAB companion with it, where we showed this curve fitting. I'll send it to you. And inshallah, I will make the second video for the SP lines. Okay, that should be a shorter one. I'll show you also, I gave you in the notes the way how you determine the parameters of the cubic SP line. Okay, that's very important because in practice we use the cubic SP line very often. I showed you in the notes how you do that. I will show another method which is probably simpler. It can be generalized how, and I'll show also a program how we determine the coefficients of the cubic SP line also. So either tomorrow, tonight I will upload this video to you, and tomorrow I'll make the other video for SP lines, upload it to you. Don't bother too much at this stage for the assessment. Just let me finish these things, and then I will show you how you send me the assignments. But work on them now, and we will do few quizzes online, and we'll see how you send them online. But don't bother yourself. What's important for me is that you understand these things and you prepare yourself, because I want to interview you. Okay? Probably before Ramadan or in Ramadan, at night, maybe after Futur, inshallah. Probably we make few interviews, okay? Every day, few, 5, 6 students. And don't bother too much. Most important to me that you understand, and you prove that you understood these things, okay? So I'll talk to you tomorrow, inshallah, okay? Thank you very much.